Go.
Okay, so the last portion of this is going to be over nuclear reactions and radioactive decay, which really kind of goes hand in hand because it talks about how when a nucleus becomes unstable, what it does. It releases these particles, which then in turn changes the proton count ultimately, which will then change the identity of the element. There are two nuclear reactions, that is two types of emission or decay from the nucleus that you need to be aware of. One is called alpha emission or alpha decay, same thing. The other one is called beta emission or decay. And biggest thing you need to know, beta emission, it's going to look like this or it's going to look like this. Because a beta particle is a negatively charged particle. And why this occurs in beta emission is that you have a neutron that turns into a proton inside the nucleus. And when that happens, you've now got this new positively charged particle in the nucleus that wasn't there before. And so then there's a negative charged particle, a beta particle released in order to offset that new positively charged particle inside the nucleus. Now, alpha emission is going to look like this, the little fish, and it is the same thing as a helium atom. So the nucleus of an unstable radioactive isotope will actually release this alpha particle, which is essentially a helium atom. It has a mass of 4 and a proton count of 2. All right, so you might see it written either way. All right, now here we're going to see the proton count go up by 1. Here we're going to see the proton count go down by 2. Okay, so this is going to actually increase it by 1, all right? And so here's going to be an example. You could see thorium, okay, 228. If it goes through alpha decay, that means that it's going to drop down in mass by 4, okay? And then the proton count is going to go down by 2, all right? Now, this is going to give you a brand new element. Either one of these are going to give a brand new element because the proton count is somehow modified. Now, if I go down 2 and we look up 88 on here, because you could be required to do this, number 88 on the periodic table is actinium, okay? Well, not actinium, excuse me, radium. All right, so radium is the new identity of our isotope. Radium will always be number 8. So number 88, it's got proton count is 88. Now, and then you also could write, you're either going to have this or this written. It means the same thing to show you the alpha particle that's released. All right, so all in all, there's a mass of 228 here, 228 on the reactant side of this nuclear reaction, 90 over here, 90 over here. You have to have balance in that count, okay? Especially if you're having to identify these numbers in a given problem. All right, now, this is where the proton count goes down by 2. Proton down 2, okay? Count is down by 2. Over here, we're actually going to see the proton count increase. So this is going to be an example of this. Could be, let's say that you've got polonium. Okay, polonium is number 84 on the periodic table. All right, and let's say that polonium goes through beta decay or beta emission. This means that we're going to, the mass number will actually not change at all because you're essentially just releasing an electron, so that doesn't affect the mass. So the mass is still going to be 212, but you're going to have an increase in your proton count. This is actually the only time. This is different over here. We're down by 2 protons. Over here, our proton count will go up by 1, okay? So we're now going to go from 84 to 85. This is going to be a beta emission, so I'm going to go ahead and show that beta particle. I could have written it in either one of these ways. And so number 85, what's that on the periodic table? Well, we find number 85, and number 85 is going to be acetine, AT, okay? So this is going to be my new isotope, same mass. Mass doesn't get affected with beta emission. All we did was actually increase to 1 extra proton in the nucleus, a new neutron transformed to that, and we released a negative charge to offset that positive charge that we adopted. And so you can see 212 over here, and then 212 over here, 84 here, 85 minus 1 would be 84 on both sides as well. So that's when you look at them in the nuclear equation sort of scenario, all right? Alpha emission, beta emission. All right, now, another way that you can kind of look at this that you might see given to you would be an isotope that goes through several rounds of different types of decay, maybe a mixture of alpha and beta, okay? Victor, are we still rolling?
Mm-hmm.
So let's say you start with polonium-212, okay? And let's say that polonium-212 goes through alpha emission, okay? This is what the fish here is showing us. We're going through alpha emission. Alpha emission is down 4 on the mass, down 2 on the proton count. So if I go down 2, that goes to 82. You need to look up and see what is 82. 82 is lead, okay? This has gone down by 4, so this is going to be 208. Now let's say that it now goes through beta emission. Let's say that now this isotope now goes through beta emission. This happens a lot. A nucleus that is unstable like this will continue to transform in order to achieve stability, okay? So let's say it goes through beta decay, all right? Beta decay means that the mass number doesn't change, okay? However, that proton count's going to change. This is going to mean that I'm actually increasing. Again, we're losing an electron, which means we gained a proton. So we're now going to go to 83 on my proton count for beta emission. Number 83 on the periodic table is bismuth, okay? And so I could continue to do this. Let's say I go through another beta decay, all right? You could do this over and over, and so you've got, what is this going to be? And then it goes through another alpha emission. What would this make the isotope, okay? So you've got to be able to, when the alpha decay occurs, bump down the mass number by 4. Bump the proton count down by 2. Goes through a beta emission, up the proton count by 1. Don't change the mass number, okay? So you can see here is a nuclear reaction occurring, 208 to 208, 82, and then you've got 82 to 83 over here. All right, we're going to say, you can see that the 83 minus the 1, that's going to give us 82. All right, but this is just another way of looking at it, is that down 2 on the proton and then up 1 on the proton, okay? So knowing what occurs there, because you could have to identify these. This would actually, at each of these sections, this would give you polonium 208. And since this would increase, this would be 84. All right, and then right here, this would end up being lead, because we're going to go through alpha, we're going to go down 2 to 82, and then down 4, 204, all right? And so you basically got this series or chain of decays occurring, whether it's alpha or beta, but those are the two you need to focus on, knowing how to, knowing the difference between them and applying them, all right? Now, so that's going to be your nuclear reactions. Other than your nuclear reactions, the last thing we're going to talk about is radioactive decay and half-lives, okay? Half-lives has nothing to do with half of your life. Half-lives is the amount of time it takes for a sample to reduce by half, okay? And these isotopes we're just talking about is what this applies to. It talks about unstable substances breaking down and becoming something new and how quickly they decay exponentially, all right? Now, let's say that you've got a radioactive isotope that, let's say you have a 2.5 gram sample of strontium-90, okay? And its half-life is going to be 28 years. Half-life is 28 years. And so the question that we're going to come up with is, in what year will it take this to get down to 0.625 grams, okay? So this is the question here. How long is it going to take strontium-90, if I start out with this much, to actually reduce down to 0.625 grams? And so this is where I said the other day in class, create a table. It's the easiest and best way to do this. We okay on time, Victor? Yeah. Okay. All right, so you create a table and you basically say, this is my amount, okay? This is going to be my number of half-lives. And you always start with 0 right here. Never put a 1, say 0, because we're starting at time of 0. Now, this is going to be like real time over here. And we have to realize that the half-life tells us, how are we counting time? We're not counting time in minutes or seconds. We're counting them in 28-year intervals. There's going to be time of 0, then 28 years. And then another 28 years would be 56 years. And another 28 years would be 84 years, I think. I'm doing that math mentally, okay? So that's what we're looking at, is how many half-lives are going by, and then we're looking at the years right here. This would be 0 years. This is 28 years. This would be 56 years. This would be another 28 years. That's going to be 84 years. Okay, so you see where we're going is that time is basically being counted in intervals according to the half-life. All right, now, how much do we start with? 2.5 grams, all right? After the first half-life, remember, every time you're doing this, you're dividing this by 2, okay? Every single time. So 2.5 divided by 2 is 1.25. So after one half-life, we've got 1.25 grams left. 28 years have gone by, half the amount, okay? Now, another 28 years, we're going to divide this in half again. 1.25 divided by 2 is going to be 0.625. So there we go. We have what we're looking for. And the question is, how long did it take? It took 56 years, okay? So you've got the number of half-lives, which is always going to be a sequence of 0, 1, 2, 3, 4, 5, whatever, all the way until you have to get your answer. And then there's the time you're counting based on what they tell you the half-life is. So let's do one more like this. Okay, so let's say that you've got actinium-226 is this, and you're going to get these crazy ice elements that you've never heard of because we're talking about the bigger ones, the unstable ones. It has a half-life, its half-life is 29 hours, okay? Weird, that's a weird value of time. See, last problem we were actually looking at years, this is actually hours, all right? So 29 hours is the half-life, okay? And let's say we start with 100 grams, okay, or 100 milligrams. So our amount is measured in milligrams. We've got 100 milligrams and the number of half-lives. So at a half-life of 0, that means that the time that's gone by is 0 hours, since we're talking about hours, all right? The number of half-lives, so we're starting with time of 0, all right? So it wants to know how many milligrams of actinium will remain after 58 hours. So after 58 hours, so I'm just going to go over here and put a question mark. After 58 hours, so we're kind of keeping an eyeball. See, last time we were keeping an eyeball on the amount, like our target amount was 0.625. So we're kind of tracking this. Over here, now we're going to be tracking this. We're just going to do what we're doing over here. And again, this is just sequentially counting the different half-lives, okay? We're going to just kind of look at when we hit 58 hours, how much do we have, okay? So, after one half-life, after 29 hours, okay, we have 50 milligrams, okay? Now, another 29 hours, 29, and another 29 goes by, that's going to be 58 hours, and so that's going to be 25. So there you go. After 58 hours, we have 25 milligrams left. So what is consistent? You're always dividing this is where we're taking it, and every time we go through a new half-life, we're dividing this by 2. Now the interval over here, depends on what the problem tells us, okay? How long the half-life is, all right? So this is going to be a graph that we're looking at for half-lives, and let's just say, okay, we're going to have our amount. All right, so on this graph, so this is going to be our, let's say, grams of our isotope, okay? And let's just say it's polonium-228, okay? So polonium-228 is what we're going to be looking at. And let's say that it's half, and this is basically what its graph looks like, okay? And so let's say, if the question could be on this, based on the graph, determine the half-life of polonium-228 based on this graph. How do you do that? Well, you take the amount and say, okay, how long did it take to divide in half? So you're basically saying, if I'm at 300 grams right here, how long did it take it to get to 150 grams? And you can see that that's around 12 years, okay? And so that means that every time, and this may not be a scale, so half of 150 would be 75, that would be another 12 years. So this would be around year 24. You can see that we've got, okay, so my graph's not to scale. I apologize for that. So, but at 75 grams, it should be around 20. So you should be able to look at this graph and see, okay, if I divide it in half, how long did it take, okay? And so another 12 years goes by, that should be a half of 150, which should be 75. And like I said, my line was probably right the first time, okay? So at 24, we've got about 75 grams, okay? So every 12 years, so you can tell that it's taking 12 years every time for that previous amount to cut by half, okay? So being able to look at half-lives on a graph like this is also really important, okay? So I think that covers just about everything. Hopefully you guys can look over your study guide, look over these videos that I'm sorry they got broken up so much, and be able to prepare properly for tomorrow's quiz. That's a wrap, Victor.